first used as fireworks and for rocket motors strapped to arrows, to being used as a propellant for early muskets and cannons. But aside from the obvious flash and bang, have you ever wondered what makes it explode? So combustion happens in the presence of these three components: heat, oxygen, and a fuel source. Where the heat provides the energy needed to react the fuel and the oxygen, which results in a chemical reaction that releases even more heat and gases. If enough heat is produced, then the cycle repeats until the fuel or oxygen runs out. And an explosion is a result of a sudden release of energy, usually from a chemical reaction like combustion. Here in our example of a candle burning, we can see that the flame heats the wax enough to vaporize it, which then mixes with the oxygen in the air and then combusts in the presence of the open flame. Now that we know what's needed to make something burn, let us look at the exact components of black powder. For the oxygen source, black powder uses potassium nitrate, and for the fuel source, black powder uses carbon. But why is this third component, sulfur, doing here? We can see here that out of the three, only the sulfur can sustain a flame when burned. It serves as a secondary fuel and lowers the ignition point of black powder. But another question would be, why charcoal? Surely there are other carbon sources that would be better, like graphite, right? Here's the thing. Charcoal, due to it being formed from carbonizing wood, ends up with a tiny microscopic holes that other ingredients can soak into. But yet another question, what are the holes for? Two words: surface area. Surface area is super important since the ingredients are only mixed through physical means and thus can only react when physically touching. To visualize this, we have here a cube where its surface area is written. If we were to cut this in half, you can see that we can get an increase in the surface area. By just grinding it smaller, we get an increase in surface area, meaning we can get more of the components touching each other. So we have here two identical mixtures. One is coarse and the other is fine. But shouldn't have the finer black powder burn faster, right? While we can see that we get a cleaner reaction due to the particles being more thoroughly combined, its speed doesn't really change that much. So why is that? Well, that's because we ground it up so fine it basically formed a block of mixture. The black powder itself burns at a slow rate, but the gas it produces expands at a fast rate. However, with our example being in an open air, the gas produced is being wasted and not helping the combustion. But didn't we mention it could explode? And doesn't exploding means it has to be faster than the speed of sound, which makes the bang? The solution to this is by granulating it with the addition of dextrin. Now with this setup, when one granules get ignited, the gas produced can pass through a tiny gaps and ignite other granules faster. But haven't we just gone back to square one with seemingly large granules? So what was the point of grinding it finely then? Well, you need to look at it this way. Before they were just individual elements toughly mixed together, resulting in a less efficient burn. Whereas in this final product, we grounded them finely to increase efficiency and maximize the burn rate, which we then granulated it to utilize the faster expansion rate of the gas, resulting in an even faster burn time. And now, with all that we've learned, let's see if our final product can finally get the ever so iconic bang from the firecrackers.
Basig di mo. Ulitan ko.